Hello everyone, here's a Physics 30 lesson. This is Unit 6, which is nuclear theory, and lesson 1 here is just straightforward nuclear physics. So 3 examples to go through. First one here is just with regards to a particular isotope, and I'm going to choose uranium just because it's so interesting. So I'm going to say uranium. And let's go 235. This is the one that, this is the enriched version. It's often used in nuclear reactors or bombs. And we are asked to determine the nuclear notation, which requires us to state the number of neutrons, protons, and nucleons. So let's just remind ourselves of the format that we need to sort of get used to using. The format goes like this. X would be, just represents whichever atom we're using from the periodic table. So in this case, we're using uranium. So I'm going to represent that as a U, which is just looking straight at my periodic table and looking at the letters there. Uranium is quite easy because it's just a U. Some of them are a bit different. So make sure you pay attention to the periodic table. Then we have we have letters A and Z. Now, A represents the number of total nucleons. Now, remember, a nucleon is whatever exists inside the nucleus. So this is going to be protons and neutrons, not electrons. So A represents the number of nucleons. Okay, and Z represents the number of charged particles or charged subatomic particles inside the nucleus. So in a sense, that's going to be just protons, isn't it? So that's the number of protons. The Z number here is the atomic number. Okay, so for uranium, that is 92. So how many protons does uranium have? 92. Okay, so that's easy. The 235, well, this is the isotope number. There's going to be different versions of uranium. Uranium 238 is normally, I think, found in nature. So if you were to chip open some rock and you happen to find a lump of uranium, it's probably 238. To get 235, you have to do some fancy stuff to it, and it's quite difficult. That's the enriched version. But these are just different isotopes of the same element. So uranium 235 is the element number. 235 is the nucleon number, the isotope number, if you like. So that's going to go here, 235. So 235 is the number of nucleons. Well, how many how many neutrons do we have? We've got protons, we've got nucleons. How many neutrons are there? Well, to get the number of neutrons, okay, we're going to have to we'll go A minus Z. Okay, in other words, the number of total nucleons minus the number of protons, because whatever is left has to be neutrons. So if we go A minus Z, that means we get 143. So there's 3 neutrons. There we go. 5. So in example 2, we start talking about binding energy. And this is where we need to be thinking about Einstein's famous E equals mc squared. We'll probably come across this more than once, and I may even talk about it later on or before this in a video where we describe the full statement that Einstein said in his special relativity. But essentially, E equals mc squared is the simplified version, and this is true when there's no movement. So this is the rest mass. Rest mass, it's often represented as m naught. It's the mass that's not moving. So we're always assuming that, and I'll try and state as many assumptions as I can in these. but we're always going to make that assumption that the thing is not moving, otherwise we get into relativistic energies, etc., which we do not want to do. Anyway, we're looking at the binding energy of copper-65. So copper-65 is the isotope name, but there's also this 64.928U next to it. So we need to visit that at some point. Okay, but let's just think about the binding energy, nuclear binding energy first of all. So we probably covered this extensively in class, but just to recap, we're going to have in our typical version of an atom, we have protons, and let's go ahead and just talk about helium here. So let's say we have 2 protons and 2 neutrons, okay, right here. And let's just say that this is the nucleus. And then we talk about the electrons whizzing around the outside, okay? We're going to ignore these electrons for now, so don't worry about those. But what's important here is that the protons and neutrons are going to they have to be attracted together, right? Because protons themselves are positively charged. So they do not want to be near each other. If we only think about the electromagnetic force, or the electrostatic force, then there's no way they want to be close together. So there must be a force overriding that, or at least significantly greater than that electrostatic force of repulsion to hold them together. And of course, that's the strong force interacting between these protons holding them together. But there's also going to be a force between the protons and neutrons, and between the neutrons and neutrons. So there's these forces interacting between all of these within the nucleus, and I think we can go ahead and just call this out as being sort of femtometer distance. Okay, that's the general range of the strong force. And what we start to realize is that at this scale, the particles are so tiny, protons and neutrons have such a small mass, and the energies are so big that we start having this mass-energy equivalence, which is Einstein's equation. This mass-energy equivalence starts to become significant. In other words, some of the mass will change into energy, and vice versa. So there's this mass-energy equivalence statement that we continually refer to here, and it's to do with the fact that the strength of the force is so strong and the mass of the particles is so small that they start becoming kind of equivalents. And what we need to do here is look at the differences between the masses going on here in copper-65 and the mass of the separate masses of all the protons and neutrons versus the mass of the actual copper-65. And we should see that there's a difference, and that will give us the binding energy. So let's think about protons and neutrons before they are bound together and after they're bound together. So I'm just going to represent that with just a simple diagram like this. Let's go ahead and say that we're just using, again, we're going to use this helium. So let's say that there's 2 protons and 2 neutrons. And we're not going to put any indication that there's any interaction between them. So these are going to be considered to be completely separate. In fact, we can let's put a little block around them. Totally separate. They're not connected in any way. There's no strong force interacting here. In other words, they're further than a femtometer apart, and so they're not interacting. Okay, so what we would do is then calculate the total mass of those things, separate. Okay, then we would take a look at what they would be like in a nucleus. Okay, so imagine that there's a nucleus here, and we've got these this force acting between them. So there's this strong force acting between all of these subatomic particles inside the nucleus. And now we can talk about the total mass when they're in the nucleus. Okay, so that's essentially what we're going to do. Now, let's think about what that might be just qualitatively before we go ahead and crunch some numbers. Let's think about what that might be, and let's imagine that we're going to put this on a scale. Okay, so we're going to put this on a balanced scale, and you've probably seen this type of thing before. So whatever goes on this side of the scale is going to be balanced out to whatever goes on this side of the scale, and we may see this move. If this side goes down, then the whatever is made afterwards is heavier. If this side goes down, then whatever is in before is heavier. Okay, so let's think about what might happen here for the before and after. Okay, well, we need energy, lots of energy for these bonds. In fact, that's what we're going to try and find out. So it's possible for me to say that I'm going to have, let's put them all separate. Oops, I'll use the colors. So we'll go proton plus a proton plus, we'll use red for the neutrons, neutron plus a neutron. So these are all separate. It's going to be equal to, now we'll put them inside. So proton plus proton, neutron, neutron inside the nucleus. Now, where's the energy? Okay, the energy is the green dots that I've represented here. This is the energy inside here. Now, does energy have a mass? Well, weirdly, yeah, it does. And that's what Einstein is saying here. So we need to somehow have energy as well as this. So I'm going to add that on. So I'm going to say plus this binding energy. Okay, and that's going to be part of my mass. So if this energy is the binding energy, and we discount it from our scale, then what this is going to look like is that when we measure the mass of the individual pieces before, it's going to be heavier. So the individual pieces are going to be heavier than the combined. Okay, and that's indeed what we find. Okay, so I'm going to put this there, neutron, neutron, proton, proton. If that's combined together, that's what we see. So this is called the mass defect. Okay, this is mass defect. It's a defect. There's a defect. Somehow there's mass missing. Where's the mass going? Well, it's energy. It's the binding energy of the nucleus itself. And so rather than it being measured as a mass, it's being used as energy. Okay, and that's what we're going to see here. Now, don't worry if that's all a bit chaotic. Obviously, it's important to know this, but there's a trick too that I can give you. And if you're getting a bit stuck, then that's where this U comes in. U is the atomic mass unit. And on your data sheet, it's given to you. So let's take a look at our data sheet and look at the mass of a proton. Okay, the mass of a proton is 1.67 times 10 to the negative 27 kilograms. And that would be the mass of an individual proton just floating around happily in space. So in other words, the mass of the proton, let's do it through here, is this guy here. Separate proton just floating there. The other value that you have on your data sheet is U, the atomic, well, let's write it as atomic mass unit, AMU, sometimes just called U. And this is basically a conversion factor. And look at the number. It's very similar, 1.66 times 10 to the negative 27 kilograms. It's on your data sheet. And this is the mass. This would be the measured mass of a subatomic particle in the nucleus once it's bound together. So this is what we're going to use, and there's much more precise values that you'll find on the internet, but this is the one that we use in Physics 30. This AMU is used when you're talking about protons or neutrons bound in the nucleus. And hopefully you can see there's a slight difference. Remember that we predicted down here, we'd said that the mass of the separate things is bigger than the combined things. Well, that's what we see here. The mass of a proton floating around by itself is actually bigger than what it would be if it was bound inside the nucleus. Okay, and that's what this represents here. This represents this U value as the atomic mass unit of copper, 65. If you measured it, notice that it's slightly lighter, it's less massive than what you would expect if you had all of the constituents separated out. So let's go ahead and solve this. Now the mass defect here, I've just annotated this. I've said the total mass of all of the things going in is MT, mass total, and the mass of the nucleus is M nuc. Okay, one more thing just to note is going to be that the mass defect is the delta M, it's the change in mass. So what I'm going to do is just compare these two masses, and I'm going to get this delta mass, this mass defect. So in other words, I can say mass total minus the mass of the nucleus is going to give me this delta M. Okay? And then if I want to know the binding energy, it's coming from this missing mass. That's the mass defect, and that's going to just be multiplied by my c squared, or the speed of light squared, and that's going to give me the total energy. So let's go ahead and figure out the masses of the copper 65 when it's separate versus the copper 65 when it's in when the nucleus is bound together. Okay, so let's first of all work out how many protons are in copper 65. Well, there's our let's go copper, and it's copper 65, so 65, and the atomic number is 29. But how many nucleons does it have? Well, 65. This is the nucleon, the number of nucleons. So that's protons and neutrons, and that's what's going to be bound inside the nucleus. So let's count them up first of all and do a total, right? So there's 65 of these guys, so there's 65 protons and neutrons, and I'm just going to go ahead and use the mass of a proton, and notice that protons and neutrons, according to our data sheets, have the same mass. That's not strictly true. If you looked at more precise values, you're going to get a bit of a difference, but let's not get into that now. Let's just go ahead and use the values that we have on our data sheet, which is 1.67 times 10 to the negative 27 kilograms. Okay, and so that gives us a separate mass, a separated out mass, an individual mass of all of the constituents of copper 65 of 1.0855 times 10 to the negative 25 kilograms. Okay, so that's going to be our total mass. I'm going to bring that over here. Let's put it in. We'll do it in green. So we have the number 1.0855 times 10 to the negative 25 kilograms. Okay, and then I'm going to subtract the mass of the nucleus. And the mass of the nucleus is going to come from my atomic, our U value, our atomic mass unit. So that's going to come down to here. So this is the atomic mass unit, the AMU. So I'm going to go 64.928 U. Now this is going to be multiplied by the U value on our data sheet. So 1.66 times 10 to the negative 27. And that's going to give us 1.07. Okay, that's a good sign because it's less massive than the total mass. 8048. Keep all those decimal places in your calculator. To the negative 25 kilograms. And I can bring that over here and do my calculation. So 1.0778048 times 10 to the negative 25. Okay, so now we can get a solution for the delta M, the mass defect. That's what we need. What is the missing mass? Well, total mass minus the nuclear mass. It's going to give us 69, keeping all these digits in here, 6952. I think I've got some more digits in there, but you can keep those in your calculator, times 10 to the negative 28 kilograms. Okay, that's the mass defect. This is where the binding energy is coming from. So now I can incorporate my E equals mc squared equation, and so I know that the energy, the binding energy, let's put that in here, binding energy is going to be the mass defect times the speed of light, which is 3 times 10 to the 8 meters per second squared. Okay, so that's going to give me binding energy. So I'm going to go this mass here, the delta M, multiplied by the speed of light squared. It's going to give me, now I've just got to check my units. I'm in kilograms, which is good because I need to be in kilograms for this equation to work, because meters per second And so kilograms, meter squared, second squared, that's joules, remember. So everything's working out well. I don't have to do any conversions. So I'm going to just put my number straight in, 6.93, okay, to 3 significant digits, times 10 to the negative 11 joules. Okay. Okay, example 3, we're determining the mass energy of a proton, but we're asked to do it in this weird unit. And you'll see this on your data sheet. This is often given as mass energy values for, you'll see it on one of the columns, electrons, neutrinos, stuff like that. Don't get freaked out by it. It's just a unit. And if we think about what it means, well, we're going to bring back our the most famous equation in science, okay, E equals mc squared, and it's a mass energy value. So if we wanted to know the mass of an electron, we could just rearrange this equation and say that it's just E over c squared, and that's really what this unit is just saying. I could measure my mass in kilograms, or I could communicate my mass in kilograms. I could also communicate it in energy per meters per second squared. Now, if I had that in joules, it would be joules divided by meters per second, meters per second squared. So, and of course, a joule is kilogram meters squared second squared, and so then you're going over meters squared second squared. Look at what happens. You end up cancelling all of these guys out, and you're left with, surprise, surprise, kilograms. So they're really the same unit. It's the same unit, just in a different way of expressing it. The only thing different here is that rather than using joules, we're using mega electron volts. Why do we do that? Well, it's just a convenient value to use. It means when you're talking about, let's say you're talking about an electron, you can call the electron, you can say the mass of an electron, the mass energy of an electron is 0.55 MeVs. And some people will just leave it there and call that the mass of the electron. Really, it's that. Okay, so let's look at a proton. So the mass of a proton, according to your data sheet, in kilograms is 1.67 times 10 to the negative 27 kilograms. That's in kilograms. We need it to be in MeV per c squared. So let's look at our E equals mc squared equation. How much energy does that have? Well, it's m, so let's go 1.67 times 10 to the negative 27 kilograms. Speed of light, 3.0 times 10 to the 8 squared. That's going to give us a value, and it's going to be in joules, because we've got kilograms, meter squared, second squareds. So that's going to give me 1.503 times 10 to the negative 10 joules. Okay, so now I'm in energy in joules. That's how much energy a proton would have if it was all converted to, if all of the mass was converted to energy. Okay, so now we're going to do a little bit of unit analysis. I'm going to get rid of the joule. Okay, I want it to be, first of all, I need it to be in EVs. Okay, so let's get rid of the joule. I need to cancel the joule out. It needs to be opposite on the fraction. And so how many joules are there in 1 EV? Well, look at your data sheet. 1.6 times 10 to the negative 19. Okay, so that can cancel out. We can do that right now. The joule cancels out. That's going to give me EVs. But I need to be in mega EVs. So let's keep going. Now I'm going to multiply it by, I'm going to get rid of the EV, so that's underneath, and now I have MEVs on top. Well, 1 MEV to an EV is a factor of 1,000,000. So again, look at your data sheet, but I'm going to put 1,000,000 underneath. I think I've got that. Yep, 1,000,000 there. And that's going to cancel out the EVs and give me MEVs. So if you do this little calculation, you are going to get your energy in MEVs, and it's something like 939 MeV. Now, that is basically it. The only thing left to do is to say that your units, let's just keep track of them. Remember your mass, currently we're in E, well your mass is just E divided by C squared. So that's really all we're going to do. We're going to take this number, 939 MeVs, but we're going to just divide it by the C squared, or at least the unit is just going to be divided by the C squared. So that is it. It's 939 MeV per C squared.